Hello, we are GatorWorks, and this is presentation one. I'm Jason Beckman.
And I'm Bernard Krasuski.
So, GatorWorks is dedicated to de-risking and developing a baseline autonomous software stack for Gator Motorsports. Gator Motorsport competes in a collegiate design competition hosted by SAE, which will compete every year designing, building, and racing a small scale Formula car against other universities. The new autonomous aspect of the competition has been recently announced, and GatorWorks aims to build a baseline software to allow Gator Motorsports to be competitive when this new category is released.
My name is Bernard Krasuski, and I'm the algorithms lead for GatorWorks. I am a senior at UF studying computer science. As algorithm leads of GatorWorks, I'm responsible for developing the autonomous driving stack spanning perception, localization and mapping, path planning, and vehicle control.
I'm Jason Beckman. I'm the simulations lead. I'm a senior at UF studying computer science with a focus on embedded systems. As simulation lead of the project, I am responsible for simulating the car and the environment to allow for rapid testing and development in a safe environment before algorithms are deployed to a real physical car. Uh, our basic project architecture diagram can be seen here. For the simulation aspect, which is my aspect, we have the physics simulator, which is responsible for rigid body mechanics and things like aero models and tire models. We have the LiDAR simulator, which is responsible for simulating LiDAR sensors and generating point clouds. And then we have the camera simulator, which is responsible for generating images. And then we have the simulation orchestrator, which is responsible for synchronizing the state of all of those simulation components together and feeding that into ROS. And then tangentially, we have the human driving simulator, which interacts with the simulation or orchestrator to allow a human driver to drive the simulation without the autonomous stack.
ROS2 middleware will be used to bridge the communication between simulation and algorithms. Vehicle state estimation is achieved through an extended Kalman filter. And coupled with the LiDAR point cloud scan mapping, we can get SLAM, which is simultaneous localization and mapping, stereo camera cone detection, and point cloud point cone clustering we use to identify cones on track and find their world locations based on the vehicle's current location and pose. And then this will allow us to utilize Delaunay triangulation to plan a generic route through the track. And then finally, we'll use an algorithm to minimize the minimum curvature and the track length for better track times.
User interfaces, as I mentioned before, we have the human driving simulator, which is a video game-esque piece of software which allows a driver to drive around a real-time simulation of the car with a game controller or a common video game racing wheel.
Arvis is a way to display sensor data and vehicle state in real time, showing kind of what the robot understands of its world. And then below here, we can see what the real world is within the simulation. And then the mission pick, this will modify the path planning and vehicle control algorithms.
Next up, we have our roadmap schedule and kind of our milestones. So coming up shortly, we have the physics simulator, which is almost wrapped up. The LiDAR simulator, which is in progress, it should wrap up the end of the month. The camera simulation, which should start soon and end the middle of March, and then the human driving simulator, which is kind of an ongoing process as things get added to the physics simulator and should be done near the end of the project's scope.
Perception will entail cone detection and processing stereo camera and LiDAR points. That'll be done at the end of February. SLAM, localization and mapping will also be done at the end of February. And then path planning should be short, so that'll be done at the beginning of March. And vehicle control, we've given a rather large buffer, so that should be done by the end of March, or yeah, March. And so far, there's been no major issues encountered in our timeline or roadmap other than mild schedule slipping.
My individual report. The physics simulation tasks have been going well with a minor hiccup in tire modeling. Due to how the tire is simulated as an infinitely thin disk, it causes the car to be very easily flippable when this is not the case in reality. The solution is to model contact patch migration in corners to stop this. LiDAR simulation tasks are also going well. Provisional raycasting math has been implemented, very rigorously tested, and a plan has been formed to use spatial partitioning to extend this to an entire scene. Camera simulation has generally been deprioritized, both to me and as the project as a whole, due to favor of LiDAR and abundance of good visual data sets. Camera simulation will build off of Bevy and the human driving simulator, and will easily extend from that. Some tasks: investigating neural tire models for modeling, investigating more standard methods, implementing logic required for LiDAR scenes, simulating a rotating LiDAR, and adapting the human driving simulator.
For my individual report, perception tasks have been going pretty well. LiDAR and stereo cameras, respective data types, are accessible and processable without any synchronization issues. And the LiDAR perception pipeline remains our POR pipeline for rapid development. For the SLAM algorithms, tasks have also been going pretty well. The car is currently able to create a 2D map of the environment by converting LiDAR scans to laser scans and feeding them through the SLAM toolbox library. And combining this with the robot localization methods allows us to build simple maps of the environment, which we can use to track, which we can use to build track boundary from the cones. Next step is to create a minimal viable product of the SLAM algorithm to map the entire autocross track with loop closing, as well as minimal viable product of Delaney triangulation for path planning algorithm. And then also to create a vehicle control algorithm which adequately uses the physics model that Jason's been working on. And this will all enable us to build or to simulate the vehicle traversing an entire autocross track, hopefully multiple times with better and better times.